Hi everyone. Welcome to video number 4 in the bomb calorimetry lab. Hopefully this will help you in your analysis for the bomb calorimetry experiment. In this video I'm going to show you how to find the corrections to delta H. I highly recommend referring to the protocol itself for the specific formulas, but I want to show you an example calculation because of all the parts to the experiment, this one is one of the most confusing, as well as one of the most long and tedious parts of the experiment. So let's get right to it. First, we're going to find delta H1, which is the first correction to the enthalpy that we found in the last video. And this part involves adjusting the reaction to standard temperature, which is denoted as T0, and it's equal to 298.15 Kelvin. That's information that's going to come in handy in just a second. Okay, so the first step to finding this correction is we're going to need to find delta Cp, which is equal to the Cp's of the products minus the CP's of reactants. So I'm going to list each of those, and it's worth remembering that Cp is equal to the number of moles of the substance times Cpm. Hopefully you remember that. So the delta Cp for this particular experiment is going to be, first I'll list the products. So the number of moles of H2O times the Cpm of H2O. This right here we found in an earlier video, but this right here is in the appendix of your book. You can find that value in the back of your book. And we'll add it to the number of moles of CO2 times Cpm of CO2. Then we'll subtract the number of moles of our sample biphenyl times Cpm of that sample biphenyl. Then we'll also subtract the number of moles of O2 times the Cpm of O2. Now, I had to go look up the heat capacity for solid biphenyl, and where I found that was the NIST website. So you can go look up what your heat capacity is for whatever your sample is. You can use NIST. Just make sure that you're using the heat capacity of the solid material at standard temperature and pressure. As long as you do that, you should be all set, but definitely also make a reference to wherever you find that value and include that in your lab report. Okay, so let's actually fill out these values. I calculated 0.030186 moles to be the number of moles of H2O that was produced in the reaction. And in the back of the book it tells me that the molar heat capacity of H2O is 75.3 joules per mole Kelvin. All right. Next, CO2. I calculated that the reaction produced 0.072446 moles. And then I multiply times the heat capacity for CO2, 37.1 joules per mole Kelvin. And that I also found in the back of my book. Now I subtract 6.0372 times 10 to the negative 3 moles. That's the number of moles of my sample, multiplied times 198.39 joules per mole Kelvin. That was the value I looked up in the NIST website. Last, oxygen, 0.087539 moles. And I looked up 29.4 joules per mole Kelvin for oxygen gas. All right, and then when I add this all together, I get merely 1.189 joules per Kelvin. That's my delta Cp. So now I do my delta H1. That just equals delta Cp multiplied times the standard temperature minus Tb, because I'm going to assume that that's a decent approximation for the change in temperature that's being made to my system. And this, when I plug all this in, 1.189 joules per Kelvin multiplied times 298.15 Kelvin minus 297.58 Kelvin. Okay, and when I work that all out, I get a very small number, 0.6777 joules. And that's it for this correction. Let's move on to the next correction, delta H2. And the purpose of this is to adjust to ideal gas conditions for the gas molecules. And in order to do this correction, I'm going to need the mu JT, which is the Joule-Thomson coefficient for CO2, and the mu JT for O2. And you can find both of these in the lab protocol. This one equals 1.10 Kelvin per bar, and this one equals 0.31 Kelvin per bar. And now I'm going to convert bars to atmospheres, and I'm going to get very similar numbers, 1.11 Kelvin per atmosphere and 0.314 Kelvin per atmosphere for O2. Now, according to the protocol, my first correction for CO2 is going to be equal to negative Cp times mu JT of CO2. And then I'm going to have two different pressures that I need to subtract from each other. And this one, of course, is just NCO2 times CP M for CO2. And when I plug in all the numbers, I'm going to get negative 0.07, that should be a 7, 2446 moles. And then I can plug in my my CPM, 37.11 joules per mole Kelvin. And then my mu JT for CO2, Kelvin per atmosphere. And then I'm going to put the pressures in the following order: 5 atmospheres minus 0 atmospheres. Now, if you look at the way I've set this up, all the units will cancel out just fine. The atmospheres cancel out, and I'm left with joules. So when I plug all these numbers in, I get negative 14 joules. And I can probably put my sig fig right there in that spot, in the 10th place. Now let's do the same procedure for O2. Before I move on to that, I want to comment about the 5 atmospheres. Why 5 atmospheres? Well, in the lab protocol it says that you can assume that the partial pressure of the CO2 after the reaction is complete is 5 atmospheres. So that's why I'm choosing 5. So now for the correction with regards to O2, it's just going to be the same formula. The number of moles of NO2, CPM for O2, and mu JT for O2. But this time, I'm correcting for the adjustment to 30 atmospheres on that side, So when I plug all my numbers, 0.087539 moles, 29.4 joules per mole Kelvin, 0.314 Kelvin per atmosphere, and then here 0 minus 30 atmospheres. Again, the units all cancel out and it works out just fine. This in the end equals 24.2 joules. All right, we are almost there. We are very, very close to being done. I'm going to get my enthalpy at standard conditions now, and it's going to equal my original delta H that I found in the last video, minus delta H1, minus delta H2 for CO2, and delta H2 for O2. So if I plug in all my numbers, I have negative 14,918 joules minus 0.68 joules minus negative 14 joules, and I'm losing track of my sig figs, but I did all this beforehand, so I should get the right number of sig figs after the fact. I add all those together, 14,929 joules for my delta H naught. However, this was for the amount of biphenyl that I reacted in the bomb calorimeter, but I want to be more general than that. I want to know how much heat is going to be released per mole so that I can scale this to any amount of biphenyl. So to do that, I need delta H naught R, which is going to be equal to delta H naught divided by the number of moles of the sample. So that's negative 14,929 joules. There's my sig fig. 6.0372 times 10 to the negative 3 moles. And when I do that math, I get 2,472,800, or that's my sig fig, joules per mole. That much heat, enthalpy is changed with this reaction. Now the final step, the final step for this whole procedure is to get the heat of formation for biphenyl. And if you look in your protocol, it's one of the first equations. It's going to be 12 moles for the heat of formation of CO2 minus 5 moles for the heat of formation of H2O minus delta H naught R. And we're leaving out oxygen because the heat of formation of oxygen is 0, as you'll find out in chapter 4. 12, and then this value I found in the back of the book, in one of those tables in the appendix. 10 to the 5th joules per mole plus 5, negative 2.858 times 10 to the 5th joules per mole, and all this minus my heat of reaction, 2.4728 times 10 to the 6th joules per mole. That's the same as this value up here. And my final answer is 3.6782 times 10 to the 6th joules per mole. Negative. And at this point, you would look this up in NIST or somewhere else and do a relative error. And I don't need to show you that calculation because you probably know how to do that. And I know this was an extra long video, but we powered through it. So thanks for watching, and I really hope this was helpful. Good luck with your labs, and if needed, you can always swing by and have me take a look at your calculations during office hours, or if we have a spare moment during maybe after class or before class, or perhaps during labs if there's time. Thanks again, and I'll see you all in lab.